Okay, so we're going to define a special type of matrix called non-singular matrix. And in this book, we've made a connection between matrices and systems of equations. And let me just tell you the upshot for what a non-singular matrix is. It's the coefficient matrix. All right, and remember that coefficient matrix is part of the augmented matrix. It's the part that does not include the constant vector. So it's a coefficient matrix of a system of linear equations which has a unique solution. Okay, we've seen that systems of linear equations can either have no solution, one solution, or infinitely many solutions. All right, so here we're talking about the case where there's exactly one solution, and it turns out that when you have that case, the coefficient matrix is a non-singular matrix, and vice versa. Right? So here, in this paragraph, he makes again the point that you can talk about matrices, you can talk about systems of linear equations. They're not the same thing, they're closely related. So be careful when you talk. When you're talking about a matrix, talk about the matrix. When you're talking about a system of linear equations, talk about the system of linear equations, and don't mix them up. They're closely related, but they're not the same thing. Okay. So for instance, you wouldn't talk about a non-singular system of linear equations, you only talk about a non-singular matrix. Okay, so let's first define square matrix. This is a fairly easy concept. You know matrix is an array of numbers, so a square matrix is a square array. It looks like a square. It has the same number of rows and columns. All right, number of rows is equal to number of columns. Okay, and if it's not square, we call it rectangular. Okay, because you can have matrices that are long and skinny, or you can have matrices that are tall like this. Okay, these are rectangular, not square. All right, so let's define a non-singular matrix. First of all, we're restricting ourselves to the class of square matrices. So you never have a non-singular matrix which is not square. Only square matrices are non-singular. Okay. All right, now suppose further that the solution set of the homogeneous linear system LS of A0 is 0. All right, now what does this mean? LS of A0. This LS of A0 is the set of vectors x, we'll call vector x, such that the matrix A times x is equal to 0. This is what we call the solution set. Solution set to this homogeneous linear equation. Now this is saying that the only solution for this particular matrix A is the trivial solution. So when you have a non-singular matrix, the homogeneous equation associated with that matrix has a unique solution, namely the trivial solution. Okay? All right, now if a square matrix is not non-singular, we call it singular. So singular and non-singular are restricted to square matrices. All right. Okay, let's go on here. Now you can look at these examples. Here he's just going back to examples. You can click back to this example and see that this matrix, when you found the system of homogeneous system, it did not have a unique solution. It had more than one solution. Okay, so go back. I invite you to go back and look at this example. And it had non-trivial solutions to the homogeneous equation. So this is not non-singular, it is singular. Okay? On the other hand, in this example, if you go back and look at this example here, you can click back and see, we found that the homogeneous linear system of equations based on this matrix had a unique solution. It had only the trivial solution. So that means that this matrix B is non-singular. Okay. All right, this example is not square, so we don't call it singular or non-singular. All right, let's go on to another definition, the identity matrix. You're probably familiar with this. This is an algebraic way of defining identity matrix. Basically, it says that the entries of the matrix are 1 if the row index equals the column index, and 0 if not. 1 if row index is equal column index, 0 if not. Now, if the row index is equal to the column index, what does that indicate? That is a diagonal entry. Same row, same column. So you can see right here, 1, 1, 1, 1. This one is first row, first column, second row, second column, third row, third column, fourth row, fourth column, okay? So that's going to be true in general. Sometimes people will write identity in shorthand like this. It has ones on the diagonal, and it has zeros below and zeros above. So that's the general form of our identity matrix. Okay. Now, identity matrix has to be square. You can convince yourself of that. Okay. Because you'd have zeros left over here if it wasn't square. All right. And notice that every column is a pivot column, and every pivot column appears once. All right. So you can see that pivot, 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 pivot. All of these are pivot columns. Each column has a 1 and the others are 0. Okay, so there's nothing but pivot columns. Okay, now non-singular matrices row reduce to the identity matrix. That's what we're showing here. Non-singular matrix row reduce to the identity matrix. Okay, so suppose that A is a square matrix and B is a row equivalent matrix in reduced form. So B is row equivalent to A, and it's in reduced row echelon form. Then A is non-singular if and only if B is the identity matrix. Okay, now think about what's going on here. If your row reduced matrix looks like the identity, then what can you say about the set of solutions? Okay, if you have a matrix A and you row reduce it and get the identity matrix, then what can you say about the set of solutions? Well, remember, when you solve an equation, so if I'm solving AX equal B, and I'll take this, I'm sorry, AX equals 0, sorry, AX equals 0, and I can row reduce this, this A to a B, okay? Wait, no, suppose B is identity matrix. Then I'm going to have 1, 1, 1, and then my last column will be zeros. Now, from this, you can read off the solution that every variable, first column gives first variable, second column gives second variable, blah, 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 last column gives last variable. Every variable is equal to 0. This first row gives me x1 equals 0, second row gives me x2 equals 0, and so on, so on, so on. Okay, so if the row equivalent row reduced matrix is the identity matrix, we can see that the solution is 0, and there's only the 0 solution, no other solution. Okay, so that proves this if part. Let me get rid of some of this garbage here. It looks like it's not getting rid. Well, anyway. That proves this if part of the statement. If B is the identity, then A is non-singular. Okay? Now we have to show the only if part. In other words, if A is non-singular, that is A has a unique solution, then B is the identity matrix. Okay? Okay, so let's think about that this way. One way you could prove this is by contradiction. You could prove the contrapositive rather. You could prove that if B is not the identity matrix, then A is not non-singular. Sometimes we'll prove things that way. In this case, he opted for a direct proof. So let's suppose that A is non-singular. And that means that if it's non-singular, that is by definition means that the homogeneous linear system has a unique solution and there's no free variables. Okay, so A is non-singular means there cannot be any free variables. Okay, now we have this relationship between the number of free variables and the number of non-zero rows. The number of free variables is the total number of columns minus the number of non-zero rows. Okay, but there are no free variables. So that means that n minus r is equal to 0, so n is equal to r. So that means that B has n pivot columns in its n columns, and that means there must be a pivot column in every column, and that's means that it must be the identity matrix, because you have to have a pivot column in every column. Where are you going to put all the ones? Okay, there's an exercise here that talks about that. Maybe I'll assign that exercise. Okay. Okay, so we can use this theorem to show whether a matrix is singular or non-singular. Easy algorithmic way of showing whether a matrix is singular or non-singular. Look at this example. This matrix A reduces to this. This is not the identity, so A is singular. Okay. Here's an example A. The matrix here is this. If we reduce it, it reduces the identity, so A is non-singular. Okay.